Welcome to a lesson with Dr. Powell. Let's take a look at an example of how a surjective linear transformation creates a decomposition of its domain. Let's take a look at this matrix right here, representing a linear transformation F, and we're thinking of it in terms of a column interpretation of multiplication for the input being column vectors coming into it. Okay, so since F is surjective, I mean, its Smith normal form is right here, and its range has dimension 2, and its codomain is R2. So F is surjective. It has a right inverse, G, and we can actually find the right inverse by looking at the column operations matrix to get to the Smith normal form and just picking out these two columns here that are associated with the ones. The column that's associated with the zeros, this one, is actually a basis for the kernel. And since this represents the function g, or the linear transformation g that goes back from R2 to R3, the columns in themselves form a basis for the range of that function g. You can think of it, well, there being two of them. It's like a plane that's sitting in R3. So when G comes back, it actually creates a plane in R3. But that plane, together with the kernel, actually span all of R3, meaning so that the kernel itself is like a line going through the plane. So perhaps we have a plane for G of R2, and let's suppose that R is the range, which is R2, say. So we're looking at, so suppose that the plane itself is G of R, and then you have the kernel is another vector coming off of this, so that the vectors in the plane and that are linearly independent and form a basis that span the whole entire space of the domain. And here's a little depiction of that. This symbol right here means that we take that we're taking the vectors in here and taking the vectors in here and finding all linear combinations or sums between them. But this right here is spanned, or a basis for this and a basis for this are actually linearly independent to each other, meaning so you can kind of combine bases from this guy and this guy, or just kind of collect them together, and it's still linearly independent. It creates a basis for the whole entire thing. This is called a direct sum decomposition of two subspaces. Namely, this is the plane and this is a line because it has dimension 1. So the direct sum of those two subspaces, so a basis for this subspace, a basis for that subspace, are linearly independent and put together create the whole space. So that's all that symbol means. It just means direct sum of these two subspaces, which means just put those bases together and just make up the whole space. This is the decomposition right here. Namely, every single vector in R3 can be written as a sum of something coming from the kernel, K, and something coming from this plane, which is the image of the, which is precisely the image of this right inverse G, as it comes along here. Okay, and so we have, right, dr is the range of F. Let's come back here and take a look at this fact. I said G was injective. Actually, G is an isomorphism from the range itself into the domain. An injective linear transformation is an isomorphism with its range, which would be G of R itself right here. Now, why is it injective? I mean, well, we could kind of map that out. Really, what we need to do is we need to show that that the pre-image of 0 is only 0. But we know something, since this is a right inverse. If you compose the map, if you do, let's see, this means that if you do this, f of g, you're going to get the identity on R2, because what is this? This is like first do G, then do F. and that's going to be the identity on R2. First G, then F. Okay, so, well, clearly the identity map, the preimage of 0 is just itself 0, so the fiber only has one thing in it. That's great. So let's think about that. So 0 comes in here, right? And 0 comes out here, and we get the kernel of F. Now, if we backtrack the kernel of F along this map right here, in any way it can, we should only get back to 0 itself. In fact, in particular, 0 is in that kernel, and if you trace that back, you're going to only 0 is what you end up with. So G definitely will be injective here. I mean, there's many other arguments. That was just one dealing with the idea of preimage 0. It is just one thing. Okay, so let's take a look and keep going here. So main is R3 is just a little picture of this setup. So K is a vector, and then you have, or it's a line, that is, in this case, it's the span of one vector. And if we take and remember that, so K is a fiber. K is the preimage of 0, in fact, of F. And all of the fibers of F, since it's an additive function, it's linear transformation, are just additive shifts of that. So a visual of that is just thinking of them as parallel lines. So all the fibers are just parallel lines to K itself. The collection of all of these fibers actually has a name. The collection of all these parallel lines, it's called the quotient space. The quotient space of D over K. So taking everything parallel to K like this, and you can fill up the whole space of D, all of R3, up with all these parallel lines. So we notate it like this, D over K. It's the quotient vector space, thinking of these parallel lines themselves as being vectors. Now, if you put a plane in it like this, such that the vectors in it and K kind of create all of R3, then this plane will not be parallel to K, meaning K will come in it at a slant, at least, of some kind, and all parallel lines to it actually, every single parallel line hits the plane in exactly one spot. And every single point in the plane can describe a parallel line. And it's a one-to-one bijective correspondence. In fact, the whole plane in its entirety can actually describes, even with its vector operations, as a subspace itself, actually describes that quotient space. So the quotient space itself is isomorphic to this plane. In fact, it's isomorphic to every plane that's not parallel to K, where you can actually hit it that way. If you think about it that way, at least planes that are subspaces, meaning that they pass through the origin. So we have this, so we can actually describe the range, or we can actually describe the collection of fibers isomorphically by that plane. And remember that this plane is actually isomorphic itself to the range, because G is an isomorphism from the range of F to the range of G, right? Okay, like as we had discussed. So actually, the range itself of the surjective linear transformation is actually isomorphic, or can be thought of perhaps as this quotient idea, this quotient space. Here's just a little example to go along with that. We can represent each fiber. So we can represent each fiber as a shift of K with a representative from the plane. All right. But of course, that particular plane depends on a couple things, on the choice of F and which right inverse we choose. We just need F to have that kernel K, right? But changing up F and G, but keeping K the same, you could change the plane perhaps. Or even if you just keep F the same and then change which right inverse we're using, then that alters which plane we're on, and alter which plane, then you alter which representatives you're going to be thinking about with the particular fibers. So, all right. So let's just say we have an element, this is a vector 1, 2, 3 in R3 in the domain. Now, if you take F and you take that in the domain, you throw it to F, and then you come back, you actually come back to something that's in the same fiber as 1, 2, 3, meaning that 1, 2, 3, and wherever you come back to, if you go this way and that way, which in this case, you get back to 1, 5, 0. You look at the notes here. So both of these go to the exact same place under the function F, meaning that when you subtract these, then you subtract their images to the zero vector. So if you subtract these, you actually get something in the kernel. And it turns out that that 1, 2, 3 is described, in this particular fiber with this representative. And so subtract these, that's in the kernel. And so we kind of get, what we do is we've decomposed our vector into a sum of two things, something in the kernel and something in that plane. So something in the kernel and something in the plane. And you can actually depict this and see what happens. In fact, with this parallel idea, this is really what we've done. We've decomposed a vector 1, 2, 3 that goes like this into a part in a plane and something that's parallel to this line right here, this K value, geometrically. And we're going to be looking at more examples to come here and just in the next sets of videos of this same idea. Thanks for watching.